Hello, everyone. Welcome to our seminar. Thank you very much for joining us today. So welcome to February talk on our seminar series, which aims to provide accessible introductions to some of the most significant mathematical theorems of the 21st century. Today's talk will last about 50 minutes, followed by time for questions and discussion. Please feel free to type your questions or comments at any time in the meeting chat. It is my great pleasure to introduce our very special speaker today, Professor Avi Wigderson from Institute for Advanced Study in Princeton, USA. Professor Avi Wigderson is a world-leading mathematician and computer scientist specializing in algorithms and complexity theory. His fundamental contributions have been recognized with the highest awards, including Abel Prize, which is widely considered as a Nobel Prize for Mathematics, and the Turing Award, which is the highest distinction in computer science and often referred to Nobel Prize of Computing. So in this talk, he will discuss expander graphs, their constructions, and their applications. So I'm now happy to hand over to our speaker.
Hi, everybody. Thank you very much, Bogdan. Indeed, today I want to tell you about these magical objects that are called expander graphs. I will define them. I will talk a lot about their applications and talk about some of their constructions, in particular, using the zigzag product, which is the reason, I guess, that Bogdan invited me to give this lecture. There is a survey book that we published 20 years ago with Hui and Linar on expander graphs. And I must say so much happened in the last 20 years that it probably needs a second edition. I don't know if we will write it or somebody else will write a more modern book. Anyway, I'll give you a glimpse of the many things that one can do with these expanders, but mention that they will not cover everything. The number of applications of these combinatorial objects in mathematics and computer science is extremely broad. You can see here the areas which are impacted by expanders in computer science, algorithm, randomness, circuit complexity, error correcting codes, networks, and many, many other topics. And also in mathematics, they are used and applied in topology, in group theory, in measure theory, in number theory, in analysis, and of course in graph theory, given that they are graphs. So it's extremely broad applications in many, many domains. So first, let me tell you what expanders are. Let's start with their definitions and basic properties. So first of all, expander graphs are graphs. Graphs are combinatorial objects. We have vertices, nodes, and edges connecting them, like if you want a network of roads between cities or communication networks between computers. We call it G. The vertex set is E, V, and the edge set is E. We'll think of the number of vertices n as going to infinity, so we will want families of graphs. But the number of connections every vertex has will be bounded by some number d. We will want very sparse networks. This will be important. And let me tell you properties of expander graphs that make them so useful. And you will see that these properties have come from very different points of view. For example, if you think combinatorially or geometrically, expanders are graphs that cannot be cut in two without cutting many edges. There are no small cuts, so it's a very, very connected graph. You can think probabilistically, expanders are graphs in which you perform the obvious random walk. You start from a vertex, go to a random neighbor, go to a random neighbor, and so on. This will converge to the uniform distribution of the whole graph extremely quickly, as quickly as possible, in about log n time. And you can think algebraically, and we'll see this in the next slide, that you describe the matrix of if you describe the graph as a matrix, as an operator, then it has a very small second eigenvalue. So I'll show it soon. My point is that all these properties are really equivalent. So we can describe these objects in many different ways, probabilistically. Oops, sorry, did it disappear? Do you see it or not? Yeah, just a second.
Yeah,
Okay. Yeah, okay, good. So this theorem says that all these properties are equivalent. Having one means having all the others. So whenever you have this, have a mathematical object which different points of view of it are equivalent, you realize already that you are talking about some fundamental object. But we'll see it in more detail. One thing about these equivalences, I want to give some of you, those that are algebraically equipped, with how these connections between the algebra, probability, and combinatorics are formed. Here's one connection: why algebraic expansion implies combinatorial expansion. This is very simple. If you represent the graph as a matrix, you on n vertices, you build an n by n matrix where if you have no edge between two nodes, you put a 0, otherwise you put 1 over the degree. So this is really the probability transition matrix of the random walk. You can study its eigenvalues, and you want to look at the number of edges that are between two arbitrary sets S and T. The matrix to think about is that this matrix, after you subtract the matrix of the random walk between any pair of nodes. Okay, and the norm of this matrix will be what we call lambda of G, is a number, a parameter that quantifies the expansion. And the way you capture it is that you can calculate the number of edges between sets S and G as a simple bilinear form on the matrix A of G. You just pre and post multiply by the characteristic vectors of S and T. And you don't have to follow this algebra, but what it says is that the number of edges between any pair of sets and the expected number of edges, if this was a random graph, is going to be very small depending on the value of this parameter lambda. But the better expander you have that the number of edges between any two sets is just what you expect in a random graph. So this is some kind of pseudo-randomness property. This deterministic graph looks like a random one. And this is one direction in the series of connections I mentioned. The other directions are a little more complicated to prove. At any rate, I want to talk about, whether such graphs exist. We just defined an object. We have to know that it exists, and we want to actually compute it explicitly. So first, some notation. As I said, we were interested not in a graph on 10 or 100 vertices, but we want a family of graphs for every n going to infinity. So we are talking about families, and my notation for expanders will be ND lambda graphs on n vertices, degree d, and delta will be an upper bound on this eigenvalue, lambda. And a graph is an expander whenever this parameter is less than 1. It's enough that it's 0.999. Then you have expansion. You have all these wonderful properties. And people realized already in the 70s that if you just take a graph at random, you pick a graph on n nodes where every vertex has d neighbors uniformly at random, then it will satisfy this property. So in some sense, expanders abound. There are, almost every graph is an expander. The main problem is laying your hand on one. So the proof of this is just by counting. It's a very early demonstration of the power of the probabilistic method, this existence proof. But what we really want is a explicit description. How do we describe an expander graph, one that we can use in the application? So there are two definitions of exactly what explicit means. Explicit means, for example, that you can just write down the matrix describing the graph in polynomial time in n. And there are stronger notions, this strong explicitness, which is used for some applications, where you have an implicit description of an exponentially large graph. How do you describe an exponentially large graph? You simply say that for every vertex, if I give you the name of the vertex, you can list the neighbors, the d neighbors of this vertex efficiently. We will not go much into the subtleties of this, but anyway, for some of you, it may resonate. Okay, so I just want to start, maybe that's one thing you'll remember if you don't remember anything else, a very, very simple to describe family of expanders. Okay, here it is. You pick a prime p, so for any prime it works. You draw a cycle on these p vertices, on these p nodes, from 0 to p minus 1. You are working mod p, modulo p. And you connect vertices to the, as you see in the picture on the cycle, to the 1 plus and minus 1 next to them. And you also add the following edges. For every x, you connect it to this inverse modulo p. Okay, so this graph has degree 3. Every vertex is connected to 3 others, and nevertheless, it's an expander. The proof of this is highly non-trivial. It's in a paper from the 80s, and it follows from some deep algebra. But the description is simple, and it states, the theorem states that this, for this graph, the second eigenvalue, this expansion parameter, is strictly below 1. It's below 0.99. So now you know that expanders not only exist, but you know at least one that's very simple to describe. And these are the type of expanders we look for, easy to describe one. Now I want to talk about many applications, and the main point I want to make is the variety, right? You will see that applications are used in all sorts of domains, and of course there'll be many others I will not tell you about. First, I want to talk about application to networks, which maybe is not surprising because graphs are networks, they describe networks. And you see that networks are used in many applications, and you see that expanders have so strong fault tolerance properties, very good communication, efficient protocols. It can be used for efficient distributed, and I'll show you also in applications to sorting. So let me start. The one basic thing you want to do with a network, communicating network, is solve the following kind of problem. I want to get from point A to point B, or I want to call somebody else on the phone or send a message on the internet. So I want a path that will realize this connection in the network. And then there may be another pair that would like the same thing, and maybe another pair. And of course, what you want is that there be no congestion. It would be great if this path, for example, are disjoint. So one thing expanders guarantee is that the path will always be short. There will be a distance at most logarithmic in n. You can have as many pairs as this allow, about n over log n pairs can do this simultaneously. Moreover, people devise protocols in which finding this disjoint path can be done dynamically as pairs of vertices enter and leave the network. And moreover, this will all remain possible if you deleted arbitrarily 1% of the edges of the node. So there are many faults. As long as there are not too many, the graph will essentially remain an expander and will allow all these applications. one particular type of communication desire people wanted is what's called the super concentrator. Here you want a network with n inputs I and n inputs O. And what you want is that whenever, it's very similar to before, but a little different, you want that whenever k can be any number between 1 and n, any k inputs and any k outputs want to be connected, there will always exist disjoint paths between them. And you want the network, again, as small as possible. And it turns out that this problem came up not in network theory, but actually in complexity, in circuit complexity. Try to understand how many edges are needed in a circuit that computes the Boolean, computes, for example, the Fourier transform. And people believe that this, because this is so strong a property, you might need n log n edges for this type, for this to happen. But it turns out that there is a very simple but sophisticated construction that gives you a linear size number of edges. So you can realize the strong communication demand just by paying a constant factor over n to get it. So this will come up, this object and its complexity will come up later and in a very interesting way. Okay. Another place where expanders were used heavily is in the question regarding sorting networks. So sorting is a problem everybody is familiar with. You have n numbers, maybe real numbers, and you want to sort them according to their order. Okay. We all know algorithms, probably several algorithms that will solve this problem using n log n comparisons. They are simple and simple to analyze and well known, and they existed forever. The question here is whether these algorithms are adaptive. They ask a question: is element number 7 less than element number 25? And you get an answer, and it's yes or no. And according to your answer, you ask another comparison. But you're allowed to be adaptive, and this is important to these algorithms. You may behave differently if the answer is yes or if the answer is no. And people were interested in oblivious, in non-adaptive sorting. And how can you describe this? You describe it by sorting network. So you can think of the n inputs coming from the left, and each time a pair of them encounters a comparator, like, for example, here, a comparator between the first and third row, between the first and third element, you imagine that the smaller one goes up, floats up, and the heavier goes down. So that's comparison basically flips elements according to their order in a pairwise fashion, like in an algorithm, but the set of comparisons is fixed in advance. You are not adaptive at all. How can you sort this way? How many comparisons are needed here? And for many years, people knew that you can build such networks with n times log n squared comparators, so a factor log n above the adaptive algorithm. And it was an open question to determine the correct answer. And Isaac Homler in this paper found that you can build such a network using only the n log n comparators, the optimal number. And this proof is extremely sophisticated and complicated and uses expanders in many ways, probably the most sophisticated use of expander graphs, which I want to highlight. Okay, let me move to a very different application, a computer science application. For that, you have to know that, I'm sure all of you know that there are probabilistic algorithms. They are algorithms that toss coins or use random phenomena to generate their sequence of operations. But random bits are actually a costly computational resources. Where do you lay your hand on high quality random bits? That's non-trivial. And because of that, you want to minimize the use of this resource of random bits. Now let's go into the application. It's called deterministic error reduction. Let me explain. Here's a typical cartoon of probabilistic algorithm. It's supposed to solve some problem on input x, compute some function of x, and it is allowed to use R, which is a sequence of n random bits. So it has access to n random bits. And suppose you buy one of these algorithms, or you get one, and you know that the error probability it makes, of course, probabilistic algorithms can make errors. It errors with probability 1/3. One pictorial way to say it is that if your n-bit string comes from a collection of 2 to the n possible strings, if you draw one at random and feed it to the algorithm, there will be some of them, some small subset of size that more than a third, will cause an error, but most of them will lead you to the correct answer. Now, suppose you are unhappy. Suppose you are unhappy with this 1/3. You want the error to be smaller. Then it's very simple to amplify, to reduce your error by repeating this experiment many times. So you run it with a random R1, with a random R2, with a random, let's say, K times, and then you take the majority vote. You believe, what most of them tell you. And it's not hard to see, it's a basic theorem in probability theory, that if you push them at random independently from this universe, these random strings, then the probability of error decays exponentially in K, in the number of repetitions. This is a very simple thing to see. But for this, you pay K times n random bits, right? You have to multiply the randomness by factor K. And in fact, it seems essential because you need independence between all these events. Somehow, amazingly, the same set of authors from the previous Alta-Commerce and Zamaradi also thought about this problem. And they show a way to save a lot in the number of random bits used without losing anything in the quality of the amplification. What they say is, look at this universe on 2 to the n objects, 2 to the n sequences, and put some expander graph on it, some degree d and some eigenvalue bound. Okay? And now, instead of picking the random strings independently, pick one, and then pick a random walk starting from this one. So go to a neighbor, to a random neighbor, to another random neighbor, and so on. And clearly, this uses much less randomness because there are only d possibilities for the next one each time. So the number of random bits is just n for the first vertex, and then a constant times k, the number of strings you need. So this is a random path. And what is amazing is that despite the high correlations between the sequences used, they are neighbors of each other along this path, the quality of the amplification does not change. You still gain exponential in k. So that's an amazing way to save on random bits using expander graphs. And there are strengthenings of this. Let me not talk about them. I want to talk about, again, a very completely different application to understand a basic question about metric spaces. So I want to think about metric embeddings into Euclidean space. L2 is Euclidean space, the normal geometry you have. Metric spaces are any spaces that have a triangle inequality on them. One you can think about is you have a graph, and the distances between vertices are defined a metric. So there are many metrics, and a metric space in general, it's a set of points x and some distance function d satisfying the triangle inequality. We say that it embeds into Euclidean space with distortion delta if there is some function, this embedding function of x, of the points in x to Euclidean space, let's say real space R to the n, if for every pair of points, the image, the distance between the image and the Euclidean distance is roughly what it was in the original metric space up to a factor delta, which we call the distortion. And a very fundamental result by Bourgain shows that every metric space, doesn't matter which, on n points, can be embedded into Euclidean space with only distortion, only logarithmic. So that's a very, very strong statement and very beautiful proof. And people ask the question, including Bourgain, can you do better? Is there maybe a better embedding? And the answer is no. By London-Lina and Rabinovich, they showed that there is a metric space that necessarily has distortion log n and not smaller. And in fact, this metric space is very easy to describe. Take any expander on n vertices and look at the distance metric I talked about, just between the points in the graph, the shortest path between them. And it turns out that this shows that this theorem is tight. And I even have a proof here. And, I will not go through it, but basically, you write down what it means for the graph to have a small eigenvalue. And this little algebra, which takes 2 lines, shows that the distortion has to be at least logarithmic. So somehow expanders capture the worst case in this basic embedding problem. And the last application I want to show you is extremely important. This is to error correcting codes, one of the fundamental problems of communication and data storage. So what are error correcting codes? This is a theory starting with Shannon and Hamming in the late 40s. We have 2 parties, Alice and Bob, and they want to communicate, but the communication channel between them is noisy. Errors are introduced. So Alice wants to send a message of length k, let's say k bits, but she wants Bob to understand it perfectly. So she encodes this message in a redundant form into n bits. So n is bigger than k, and sends this message, and then this message goes along the channel to Bob. Now, because the channel is noisy, some small fraction of the entries of the message into the n-bit message are corrupted. Maybe they are flipped, okay? Maybe 1% of them. And then Bob gets this noisy version of the message and has to decode it back to the original one. So this is what error correcting codes are. And the key parameters of error correcting codes are the rate and the distance. Rate is k over n, is roughly the redundancy you have to pay in order for correcting errors. And on the other hand, the distance of the code. The distance of the code is the distance, the Hamming distance, the number of different positions between any code words. So C of x and C of y are the encodings of x and y, respectively. Why do you want them to be far apart? Because you want to tolerate errors. If they are very, very different, and I send you x, and I send you x, so you get C of x. C of x, if you corrupt few bits around it, you will still not confuse it with the encoding of something else if the distance is high. So, the gold standard is to have a good code. Good code means that the rate is constant. You just pay redundancy, which is a constant factor, and the number of the distance of the code is linear, is as big as it can be. It's some constant fraction of all entries. So that's what we want. And Shannon, again, in one of very early demonstrations of the probabilistic method, showed that a random code, if you pick code that's random, then it will be good. But of course, this is not very helpful if we want to use codes. We want to have a very explicit description of the code, right? And moreover, we want to have very efficient algorithms to encode and to decode codes. Okay. This took like 20 years to first get some explicit and efficient constructions. They were mostly algebraic, starting in the 60s. And around the 80s, well, actually already in the 60s and more so in the 80s, people also developed combinatorial constructions, starting with Gallagher for building good codes. And what I want to, maybe one highlight of this effort in the combinatorial setting is the result of Dan Spielman, who found an explicit code that has optimal encoding and decoding time, namely linear time. In linear time, you encode and decode. I will show you something close to that, but I just want to point out that his inspiration came from the construction of superconcentrators, which I mentioned in the network applications. Okay, so I want to give you 2 slides explaining roughly how this is done. What do expanders have to do with codes? How do you generate codes from expander graphs? So this is what we want. And what Gallagher already suggested, he wants to say, take an expander or something like an expander, which is bipartite. It has 2 layers. One is of size n, and the other of size n to the k if you want to send k bits to n bits. What is the way you encode? Or first of all, let me define the code. How is the code defined? I want to tell you when in some particular sequence z of length n is in the code. It is in the code if it satisfies a bunch of linear equations that are derived from this graph. Imagine you put a linear constraint on every node on the top, and what you demand is that the sum of its neighbors in the bottom is 0 for all the output nodes. Okay, so this is some linear, it's called the parity check, this system of equations. You say that the z is in the code if p times z, this parity check matrix, which captures these linear equations, is 0. So it's a linear code. Okay? It's a linear code. Again, z is in the code if p times z is 0. And what do we want? We want that it will be a good code, right? So let's slowly talk about the properties. The name for this type of code is LDPC codes for low density parity check matrix. So in the equation, because the degree of this expander is small, it's a very sparse graph, so the parity matrix has very few non-zeros. It's really trivial to see some properties. For example, because we have n minus k equations, there's still k dimensions we didn't touch, so the rate of the code, we can encode k bits into n bits. The encoding time is just computing a linear transformation, right? The code is linear, so to convert an input to an encoded form is just computing a linear transformation. Certainly can be done in n squared time, and in some cases much faster. What is more challenging is to see that this code is high distance, and moreover that you can decode it from errors quickly. And what I want to show you is that certain expanders, certain so-called lossless expanders, which I'll define next by example, if you have such expanders, then you immediately get these properties, okay? So let me do that. Lossless expanders are, I didn't show you one, and it's more complicated to construct. And here the particular parameters, you can, the first construction was in a paper I had with Capalbo, Reingold, and Vadan. this lossless expander. So to pick fixed parameters, let's say that we want k to be n over 2, so we just want redundancy to be doubling. And what do we want? We want, from this graph, the property of being lossless means that every small set of vertices in the bottom see as many neighbors in the top. So here I picked in this example the degree to be 10 in the bottom. So what you would like is that every small set B in the bottom, B may be the corrupted set later. Anyway, any small set B of vertices will have many neighbors, almost as much as possible. The maximum is 10 times the size of B, so it's 9 times the size of B, let's say. This is lossless. It almost loses no output nodes. If you think about it, a typical node in B, we'll have 9B out of the 10B. We'll have 9 out of the 10 vertices in this union of neighborhoods. So neighborhoods of vertices in B are almost disjoint, which is really great because we use it. Here, this is what, if this is a set of errors, of course, how are we going to correct? We have to use the definition of the code. We can always compute these linear equations. Of course, if the given word W is not in the code, it has some errors, then we will not get all zeros at the top, we'll get some ones. And they should indicate for us where errors are and how to correct them. And what you do is a simple greedy process, which is already implicit in a paper of Spillman. What you do is the following. You look at the outputs, and you look at the nodes that are labeled 1. These are things we don't want. We want them all zeros. And you can say if a node is labeled 1, if I flip, I look at nodes in the bottom. Of course, I don't know which are the errors, but I look at the bottom and look at its neighbors upstairs. If more of them are ones than zeros, then maybe it is an error. Maybe it is causing error, given that neighbors are almost disjoint. It may be responsible for an error, then we flip its value. So this is a very greedy procedure. And what is really easy to show is that if you start with some set B, which you don't know, and you do this operation once, this majority correction, this number will shrink by a factor of 2. The proof is, is really easy. Of course, you reduce errors, but maybe you generate others, but overall, you shrink the number of errors by a factor 2. So this will converge in logarithmic time and actually in a linear amount of work. And because B can be as large as 0.5% of all inputs, this is the number of errors you allow. This means that the distance between any two code words must be at least 1%. So it's a constant fraction. That's an extremely simple way of using expanders to lossless expanders, I stress, in order to build essentially optimal error correcting codes. So they are powerful here as well. Okay, now for the last part of my talk, I want to go back to explicit constructions. I already showed you one particular explicit construction, algebraic one, of expanders. It turns out, and I'm not going to read this slide, by now we have many methods of designing expander graphs using various algebraic or combinatorial tools. And what I want to talk about is the zigzag product method to construct expander. That's a theorem that Bogdan wanted me to discuss. So the one thing the zigzag graph product did for the first time, now we have more methods, it allowed to break away from the algebraic constructions of expanders and offer a combinatorial construction of expanders, and actually a very simple one with a simple analysis that does not depend on deep results in algebra or number theory as previous ones used. Okay, so what is this zigzag product? first it appeared in a paper with Reingold and Vadan, who at the time were my postdocs here at the Institute. It's a product of two graphs. So there are many notions of graph products in graph theory. This is a particular one, new one. Imagine I'll give you two graphs, G and H. Think of G as a big graph and H as a small graph. So you notice that G has n vertices and degree m can be large. M will be the number of nodes in the small graph. So there is this compatibility. The number of nodes in H is the same as the degree in G. And they have some bounds on the eigenvalue, alpha and beta. Okay, we want to combine them to build a bigger graph, which is still an expander of some quality. So this is done as follows. So imagine that H is this simple graph, just for the picture. What you do is you put a copy on H around every vertex of G. So here is how I define the zigzag products of G and H. The vertices will be pairs, a vertex from G and a vertex from H, and they come, as I said, by placing a copy of H around every vertex of G. So here we have some local picture of V has some two vertices, G has some two vertices, V and U connected by an edge. After I put this copy on H, then I get these, I create these new edges, both edges of G and edges of H. And now I want to forget about these edges and rather connect these, when I make a small, that's the origin of the word zigzag. If I'm at a vertex, I want to know where my neighbors are. I simply walk along one edge in H, then switch to the other side of the blue edge. There is a unique one to a cloud around U, and I make a small step in H in this cloud. Okay, so this is the description. All these will be edges in my new graph, the zigzag products of G and H. And I'm not going to quite prove it, but I really stress that it's not complicated. That what you get out of this is best of both worlds. You get, first of all, a bigger graph. It's the size is n times m, so you created from these two graphs a graph that's bigger. The degree will be d squared. That's easy to see because you make just two steps on the small graph and you are deterministic on the part of G. So it doesn't matter how big the degree of G was, it will disappear when you look at the zigzag product. So there's a method to reduce the degree. And you suffer a little bit in the quality of the expansion. You get the sum of the bounds on the eigenvalue alpha and beta. The reason this is not so bad is that you can immediately fix it by squaring this graph and reducing the eigenvalue. So without details, the theorem says that the zigzag product is an expander if and only if its constituent are, and basically of the same quality. So the way you get an infinite sequence of graphs is you start with H, and basically, and G equals H, you have to start from a small constant size expander, and now repeatedly apply this operation, creating bigger and bigger graphs, and each time take the last graph and zigzag it with H and get an even bigger graph. They will all have a fixed constant degree, d squared, and will all have a good spectral bound, so will be expanded. And it's an elementary proof. This iterative construction of expander is different than the other ones. There are many consequences, not just, this particular construction of expanders turns out to have many consequences. I'll just mention them briefly. You can use them to build lossless expanders, I mentioned before. There is a connection to algebra, so even though we broke away from algebra, this construction we observed in a paper with Alon and Lubowski is connected to semi-direct product of groups. In fact, Zigzag product is sort of a combinatorial generalization of this group theoretic notion. And because of this, you can apply the zigzag product to create not just expander graphs, but expander Cayley graphs, namely graphs on groups. And there are these two papers which create such expanding Cayley graphs for non-simple groups. We know about simple ones, but these were new. There are also many computer science applications. I'll show you this one, so I'll talk about it soon. It led to a very simple and different proof of the famous PCP theorem by Dinu. It allowed to construct codes with very essentially tight connection between the rate and the distance by Amnon Tashma. It allowed to build Ramanujan generators. These are generators that are a nearly optimal eigenvalue for almost every group. And it also had implications on what's called property testing that I will not explain. So you see, even not just expanders, but expanders constructed using the zigzag product and the analysis of the zigzag product itself led to really interesting consequences. This is a good point to make that sometimes even when you can solve a problem, having different solutions is useful. Zigzag product was a different way of constructing expanders, and this way of constructing them turns out to be useful to applications which cannot use just any expanders. I want to talk to you about this SL equals L result, about escaping mazes, and that's almost the end. So what is this SL versus L question? These are complexity classes in complexity theory, but it really asks about low memory algorithms for navigating networks. Okay, so navigating mazes, unknown terrains, or getting out of mazes is a very old problem, and it appears in Greek mythology, but also a basic problem when we explore other planets, for example. And there are very good algorithms to explore graphs, but here we want to stress that you are using a minimal amount of memory. You are allowed, if the graph is of length n, of size n, that has n vertices, you want to use an amount of memory that's only logarithmic in n. So what you are allowed to remember is basically the name of one vertex or of 10 vertices, and that's all. And nevertheless, you want to navigate this terrain. So one way to think about it is you land in some unknown city, and you want to go to a pub, and you don't have a map, and you cannot use a map. You are just allowed to wander around. And one way of doing it, which is suggested in this theorem, is that you walk randomly. If you walk randomly, you don't need memory. You just need to remember where you are and what are the names of the streets next to you. This theorem from the 80s says that a random walk on any graph, just any graph, if it has size n, walk randomly for n squared steps, you will discover not only one pub, but you will discover all pubs. And in fact, you will visit every corner in the city in n squared steps. This will happen with extremely high probability. So there is a solution here. We can navigate any terrain if we allow random bits. We need to be able to toss random bits. The question was, I mentioned already that random bits are costly. Can you do it without random bits? Is there a deterministic way to get out of every maze and to visit every city? And that was, stayed for a very long time, indeed until 25 years, until zigzag existed. Omer Reingold discovered, using zigzag, that you can construct a deterministic walk, also of polynomial length, right, which you can generate in log space with just the minimal amount of memory, and you just, rather than walk randomly, you walk according to the instructions of this walk. It tells you to go straight, right, left, backwards. And using it, you just one walk will visit every city of Flemington, completely visit every corner of it. This, in complexity terms, this is stated as SL equals L. But that's not very important for us. And as I said, this uses analysis, construction and analysis of zigzag expanders. Okay, let me end by saying that I talked about expanders, the classical notion. There are many, many other variants of expander graphs. There's a linear algebraic one called dimensional expanders. There's a quantum version, which is called the quantum expander. There are monotone expanders and many others. And just to highlight a recent development of the past decades or so in extreme speed, notion of high-dimensional expanders. These are not graphs but complexes, simplicial complexes, which in some sense expand, and they can be constructed, and their construction led to resolution of long-standing open problems recently, in particular constructing locally testable codes, quantum codes, and analyzing all sorts of Markov chains. Here, unlike normal expanders, there is no abundance at all. Random graphs or random complexes will not be expanders, and constructing them requires still heavy algebra. Let me conclude by advertising this book I wrote. It's about computational complexity and more generally the theory of computation. It's an invitation to my field. It's written for people who are just interested. You don't need to know much. And also you don't need to buy it because it's free on my website and you can access it at will. Thank you very, very much.
Yeah. Okay. Thank you for nice talk. I will now allow everyone to unmute themselves and also turn on cameras. So everybody is welcome to unmute yourself and ask questions and also turn on cameras. So I have few questions already in the chat. So Frank Morgan asked, in your example, which we should never forget, first explicit algebraic constructions of expanders, it should be three regular graphs. So 0 should be connected to 3 neighbors.
Yeah,
so what is the third neighbor when 0 is connected?
Yeah, it's a minor point. You can connect it to itself. You
can connect to itself. Yeah. Okay.
Yeah, it's a minor point.
Okay. So another question from chat was, in what sense you were talking about almost every group? So
almost every group or almost every graph?
Almost every group. On one slide, you mentioned one of the applications that almost every group has some generators or whatever. Yeah. So
I almost okay. Yeah, I don't remember this slide, but let me just say about, first of all, almost every graph is an expander, and almost every group, for every group, a random set of generators of size not constant but log n will be an expander. These are two statements.
Okay. So I see another question just came from Ismail. Thank you, Professor Avi, for the very informative seminar. Are there any interesting theorems concerning clique complexes of expander graphs? I am interested in K homology of the induced clique complex.
Yes, so the comment I made in the previous slides about high-dimensional expanders, these are complexes, and in fact, many of these complexes are themselves clique complexes of graphs. So it is true, you can search the literature for high-dimensional expanders. Some of them are clique complexes of expanded graphs, but not every clique complex of an expanded graph is a high-dimensional expander.
Thank you. I also have my own question. You had a long list of explicit constructions of expanders, and some of them were much later than your zigzag product paper. So my question is why we need so many explicit constructions? Like in math, if the theorem is proved forever. So we have your zigzag product construction. So we have explicit construction of expanders as large as we need for any applications. So why we need so many other explicit constructions?
So as I mentioned, you never know what a different proof of a theorem will do for you. I'm all for having many different proofs of theorems and many different constructions of important objects, because you often the ideas in a different proof lead to different progress than the idea in the older proof. And the ideas in a new construction often have applications that were not existing before. I mentioned in this slide a long list of applications of zigzag expanders that cannot be obtained by previous expanders. So in general, having many proofs of the same theorem and having many constructions of the same object, especially when these are important theorems and objects, can enrich math just as much as the first proof of a theorem.
Okay, yeah, thank you. So any other questions, please? Yeah, I see one more question. Anything to say about the 18th example of isometric profile not continuous via expander graphs?
Can you repeat this, everyone?
Can you just click on chat button and read it yourself?
Maybe.
It was by Papa Soglu and Swenson in 2018. They used expander graphs to give a 2D example of an example of a 2D space for which the isoperimetric profile failed to be continuous.
I don't know this result, so I cannot comment on it. But there are many applications of expanders that I don't know. There are related things. I think that the one you mentioned that were first developed by Gromov, and they are related in some way to what I mentioned about metric embeddings. I don't know if this is the source of your example, but anyway, I don't know this one.
Okay, thanks. Just more testimony.
Yeah. Okay, any other questions, please? You can just unmute yourself and ask. Okay, if there is no more questions, we are almost exactly 1 hour, so we are exactly on time. So just thank you very much to our speaker, to Avi, for this interesting talk and for accepting invitation. And thank you everyone for coming. And the next seminar in the series will be in March, 4th of March by Professor Asaf Naor.
Thank
Okay,
you very
yes.
much.
So.
Thank you, Professor.
Bye-bye. Thank you.